This is the video for our 6.4 notes. It is already filled out. I'm going to go through kind of quickly, so if you need to pause at any point, I encourage you to do that, or you may even need to watch certain parts a couple of times to make sure that you're completely understanding. So exponential growth and decay. We've already talked about exponential equations are of this form. This should probably really be y equals a times b to the x. Actually, let me just change that real quick. Of the form y equals a times b to the x. So we're going to start looking a little bit more specifically at these equations, and we'll notice that this a value is going to be like the initial value, and then this is the growth factor, because this is what keeps getting multiplied over and over by the exponent. In exponential growth, a has to be greater than 0, and b has to be bigger than 1. So we can think about this another way, and in your practice it will show some of these examples where this is split up like this as well. So we can split that b value up like this. Since b has to be bigger than 1 for growth, however much bigger it is than 1, we're going to call that our r value, which is our growth rate. Right, so however much bigger that number is than 1, that's what we're going to call our growth rate. So for example, if we have this equation right here, a is 100, that's our starting value, and then I'm multiplying that by 1.06 to the x. So if you notice, this is, I've got 1, but then the additional amount is that 0.06. So that r value then, that's the 0.06. As a percent, that's 6%. So for every 1 x goes up, our initial value is going to increase by 6%. So you'll see this in the practice, either written like this, or sometimes they're going to break that up and they're going to write it like this: y equals 1 plus to the x. Okay, so that's what that would look like if it was actually broken up. We would have 1 plus that 0.06. Sorry, that didn't come out very clear, but that's what that is, 0.06. So when you split it up like this, this really shows that that is that r value, that's that growth percent. So get rid of that because that's just a little bit messy there. So example 1, the inaugural attendance of an annual classic music festival is 150,000, and the attendance increases by 8% each year. So inaugural means the first time something happens. So the first time they held this music festival, they had 150,000. And if the attendance increases by 8% each year, this is how we would write that equation. Right? We've got our initial value, and then this is our growth factor, with that being the rate. That would be the r value right there. That 8% is how much it's growing each year, to the t, because it asks for attendance after t years. And a lot of times in these equations you're going to see that variable as a t, because we're talking about some form of time. And this makes sense because if we talk about year 1, okay, so year 0 is 150,000. Year 1 would be 150,000 times 1.08 to the 1, which would just be 150,000 times 1.08. The times 1 gives us our original value. And then that additional 0.8, that represents the 8% growth. And then if we had 2 years, we would be multiplying by 1.08 twice. 3 years, we're multiplying by 1.08 3 times. And that's where we get that exponential growth, where we're growing on the initial value and then every value the year after year. So this is asking how many people will attend in the 5th year. So that means I'm just going to let that exponent, that t value, equal 5. I'm going to punch this right into a calculator, and here's what we would get. So in the 5th year, we would expect an attendance of 220,399. Exponential decay is when we're getting smaller. So we still have this same form, y equals a times b to the x. A still has to be bigger than 0. But now this b value is going to be between 0 and 1. And this makes sense if we think about when we multiply by 1, again, that's going to give us the same number over and over and over. If I multiply by something bigger than 1, our original value will get bigger. But if I multiply by something like 0.5, so take, for example, like if I have just 8 times 0.5, that's going to give me a smaller number. Specifically, that would give me 4. So if I keep multiplying by a number between 0 and 1, I'm going to keep getting smaller and smaller and smaller. So that's what exponential decay is. We can rewrite this in a slightly different form as well. So now we're going to have 1 minus r, where this is the rate of decay. And our example, again, on the right, so if we have an initial value of 100, and I multiply by 0.75, I'm going to get like 3/4 back. So when x is 1, I would end up with 75, and then when x is 2, I would end up with 75% of 75, and it would just keep going in that way. So if 1 minus r, so that's this value right here, if that is 0.75, that means our r value, our rate of decay, is 25%. We're shrinking by 25% every time. And so, again, in the practice, you might see this written as y equals 100 times 1 minus 0.25 to the x. Right, so these represent the same thing because 1 minus 0.25 is the same as 0.75. So just depending on how it's written, it may, you just have to think about that r value in a slightly different way. All right, identifying exponential growth and decay in a table. So we talked about earlier how we know that function is exponential when we look at a table. If we have x that has a constant difference, but then our y values are either being multiplied or divided by a constant number. It's going to be decay when we're doing division, or as x gets bigger, y gets smaller. But that y is going to need to be smaller exponentially. So in this case, dividing by 3, or that would be the same as multiplying by 1/3, depending on how you think about it. But as x gets bigger, y gets smaller in an exponential fashion, so being multiplied. And if we are growing, if we're looking at exponential growth, they're both getting bigger, and as x is added to or has a constant difference, the y values are being multiplied, and both are going up. If you remember linear equations, they're both x and y going to have a constant difference. So this would be like +1 + 1 + 1, and the y values would either be like +2 +3 or -5 or whatever. It's all going to be addition and subtraction, whereas exponential, you're going to have your y values being multiplied. All right, interpreting exponential growth and decay. So determine whether it's growth or decay, identify the percent rate of change. So that's that r value again that we talked about up above. So this first one, we're always of this form, y equals ab to the x. So this 5, that's my a, that's my initial value. Here's my b value. We have that, we can think about that kind of being broken up. It is growth because b is bigger than 1. And if 1 plus r is 1.07, then r must be that 0.07. That's how much bigger than 1 that b value is. So 0.07, that's the same as 7%. So to get from a decimal to a percent, we just move that decimal place 2 places, because percent means out of 100. So 0.07 is the same as 7 out of 100. So this would be rewritten if we were going to split this up. This would be y equals 5 times 1 plus to the x. Second one, if we look at our equation here, we know if it is growth or decay, again, by this value here. This is between 0 and 1, so we know that it's exponential decay. If we're looking for the rate of decay, this is where we have to do a little bit more thinking, I feel like anyway, than in the growth model. If 1 minus r is 0.98, so that's what we're multiplying our initial value by, that means we have a decay of 0.02 or 2%. Because if we want to write this in an equivalent way, we would have to write y equals 0.2 times 1 minus 0.02 to the t. So again, notice that this b value is the exact same as this b value. It's just written in a different way, which tells us that this is that rate of decay.